Yeah, hi everyone. Today we have Samir as our speaker. He's talking about his recent work, Spiral, fast, high-rate, single-server private information retrieval via FHE composition. Let's welcome him.
Hi, I'm Samir. This is joint work with David Wu at UT Austin. So our work is about PIR. So I'll start by just kind of talking about what PIR is. So in private information retrieval, a client wants to retrieve a record from a database without letting the database learn which record they retrieved. And crucially, this should hold even if the database is malicious. We consider this single server setting where there's one database and we're trying to protect against that one malicious database. We examine this setting because it's a basic building block in many other privacy preserving protocols. So an example, if you want to think about what the database could be, you could imagine the database is a DNS table, or you could imagine that the database is an encyclopedia. And the idea is, which item the client is retrieving is the thing that we're trying to protect. The data, in some ways, the metadata that we're trying to protect. So when evaluating a single server PIR scheme, there's like 4 key metrics that you want to look at to see if it's kind of practical. The first is the size of the query. So that's the size of the query that the client has to upload to the server. The second we phrase as server throughput. So this is a kind of computed metric on the server's computation time. And the reason I use throughput here is because without pre-processing, without some kind of fairly recent, mostly theoretical work, the server needs to perform a full linear scan over the entire database to answer a single PIR query. So one way to think about that computation time is throughput, where we say that we need to process the entire database. So how fast are we doing that? What's our throughput? The other metric is rate. So here, this is another computed metric. Basically, it's the ratio of the actual database record size to the response size. So typically, in these schemes, there's some kind of blow up. You have to download more bits than you're actually retrieving from the database. So the rate is a measure of that ratio. And there's like a fourth cost that's not always kind of concretely documented by everyone, which is the public parameter size. So what we allow is the client to upload some data to the server that we assume the server stores kind of for the duration of the client's interaction with the server, and is useful for some unbounded number of queries and not dependent on the database size. So these public parameters, it's a useful cost to look at because in a scenario where you have many clients, this could be a significant cost to keep all of these around in storage and memory. So yeah, but these are the 4 costs we look at.
So why do you use this database size over server computation? That seems a little bit unnatural. Like, why not just use server computation as a function of n? And usually we just talk about server computation as a function of the database size n, right?
Yeah, the reason to think about it, I mean, throughput is just, I guess, a way of measuring it. But the particular reason we measure it as throughput is kind of to just make a comparison across schemes and database sizes consistent. So you could think of it as throughput for the number of database items. You could also think of it as throughput for maybe the size of the items, but we want the total database size, so the total number of bits in the database. We want that ratio so that we can compare more easily. Does that make sense?
I don't think we should dwell on this point because I feel like server computation just as a function of database size, you can compare among different schemes too. But maybe it's like a tangential point there.
It might be clear from like the table on the next slide. So we introduce a family of PIR protocols that we think use FHE composition to get better results in single server PIR. We select our parameters automatically based on the database configuration, and we achieve significant improvements in all 3 key metrics at the cost of larger public parameters. So here you can see I've like phrased throughput as in like megabytes per second. So this is like, we have a 2 to the 14 record by 100 kilobyte record size database. And we're processing the database at a throughput of 300 megabytes per second. It's kind of useful to think this metric in relation to other hard limits on throughput of computation. For example, memory bandwidth is always phrased as gigabytes per second. And we'll see we get pretty close to memory bandwidth. So you can see our query size rate and throughput are all better, but the public parameters are larger than previous work. This is compared to the best previous work. All our measurements are single thread, single core. And I'll just show that we also have a streaming version of the scheme where we make the query much larger. This makes sense in scenarios where the query is fixed, but you want to change the database. So for example, you can imagine streaming a video, say. And here you can see that the throughput is at 2 gigabytes per second. And the reason it's useful to use this throughput metric is because this is roughly 5 times the throughput of software AES. So just like in your head, if you're thinking, how fast is PIR? We have to do a linear scan over the database. How fast is that linear scan? Well, it's 5 times faster than if you were doing AES without hardware acceleration. And it's only about 5 times slower than memory bandwidth, than the fastest possible we could do on a single core. So our throughput is kind of within striking distance of almost the best you could really hope for. It's only 5x lower than the best you could hope for. And it's 5 times faster. Yep.
Isn't comparing with scanning through the database using AES, that's like a pretty poor baseline, right? If the database is big, why do you want to make an AES pass over the database?
No, it's not a baseline like you would do this instead of this. It's just that I think for reference, this is like a public key like homomorphic type operation. So in the past, a lot of PIR work has distinguished between like applying a symmetric primitive versus public key operations, and said like our PIR scheme minimizes public key operations. And what we're showing is like there's sometimes maybe that assumption that all public key type operations or all like homomorphisms are somehow slower or than applying a symmetric primitive. So the other thing I want to say is the rate is also very close to the best we could hope for. So the rate is the best we could hope for, and the rate is 1, right? And we're able to achieve 0.81. So that's really high. And in scenarios where we are communication cost constrained, where the cost of communication dominates, this means that the cost of delivering privacy is less than 2 times the cost of direct retrieval from the database. So for AWS cloud computing, we are less than 2 times as expensive as actually just directly retrieving the movie you wanted to watch, because communication costs are the primary costs in that scenario. We also like to show off that the work is practical. We have a demo. So you can read about a third of Wikipedia over PIR if you go to this website. It's pretty fast. It's like the first query takes a long time. It takes like 30 seconds, but all subsequent queries take about 4 seconds. And the reason the first one takes long is you have to upload those public parameters that I mentioned. We think this is a cool way. Yeah.
So when you say it's twice as expensive as downloading the movie in the clear, you're talking about the response time, right? Because if the server is running PIR, the throughput will be much smaller than server just serving the content in the clear.
Yeah, I'm not talking about, I'm talking about cost, server cost, monetary cost in dollars. So the server has to pay some cost for compute and some cost for outbound communication. And we're saying that the total server cost of not privately streaming the data and privately streaming the data using our scheme, the differential is only 2x. Does that make sense?
No, I mean, I just wonder like how to make sense from this, because like let's say your scheme needs to linearly scan through the database for retrieving a movie. Are you doing batching?
No, it's a single query.
This is single query. So if you serve the content in the clear, you only have to, let's say the movie is 1 gigabyte. So you only need to look at gigabyte.
Right.
But your whole movie database can be, let's say, hundreds of terabytes.
Yep.
Are you saying reading hundreds of data bytes is just twice more expensive than reading 1 gigabyte? That seems like unlikely to me.
Well, the database isn't quite that big. It is 2 to the 14 movies. But yes, what we are saying is that the throughput on a single core is fast enough that if you think about computation as a cost rather than a time thing, right? I mean, you just pay on a cloud computing instance for CPU seconds, and this problem is naively parallel. So you can think of the processing that we have to do as just a cost, right, in dollars. So what we're saying is that cost in dollars is very small compared to the cost of actually sending the movie back to you, you know, like in sending the 1 gigabyte.
Give more breakdown of how this 2x is computed, because I think if that's true, that's really interesting, because you are saying there's just like 2x more cost. But somehow this number is very far from something that I can mentally imagine. I think there's something like in the ballpark that I'm missing.
Sure. I guess here's the way to say it. The cost on AWS to stream 1 gigabyte to you is like is equal to the cost of like hundreds and hundreds of seconds of CPU time. So the computation is just much, much cheaper than communication. And so if you think about the cost to stream the 1 gigabyte movie to you, our scheme, when you use PIR, it only takes, say, 1.2 gigabytes to stream to you. The communication overhead is quite small. And there is some computation associated with like processing 2 to the 14 movies. It's just that overhead is on an absolute basis in cost quite small.
So let me ask you, in your experiment, are you only considering 1 client and 1 server? So what about, let's say, I want to serve 10,000 clients at the same time? And like, you know, now there's the question, if you are serving in the clear, 1 server can serve 10,000 clients, but now if you are using PIR, 1 server can only serve 1 client. So which scenario are you in when you computed the 2x?
Yeah, when we compute the 2x, we just phrase computation as fully fungible. So we just say that like you need to perform X CPU seconds of computation. So we assume that like at a cloud provider, you can just dynamically choose the number of CPUs you want and process the query that way. So if you're saying that like we assume that the CPU cost of serving a movie non-privately is 0. And we assume that the CPU cost of serving the movie using PIR is quite large. It's just that it's very small.
But there's still the difference. Even if it's 1 CPU, I think 1 CPU can serve many clients in the
it can serve an essentially infinite number of clients. I mean, yeah, in the non-private scenario.
But in the private scenario, 1 CPU can only serve like a small number of clients, let's say 1 client.
Mm-hmm.
So how is that counted, like when you computed the 2x?
What I'm saying is like you can, so like, let's say that 1 CPU can serve the client's query in 5 seconds, right? We agree that two CPUs can serve the client's query in 2.5 seconds, right? So we make this like assumption that the problem is totally naively parallel. And then we say that like the total amount of CPU time needed to answer a query is some number. Even that total amount of CPU time is in the movie example, some hundreds of seconds. That's in dollars and cents in cloud computing costs. That's not very much compared to the cost to stream the 1 gigabyte.
I see. So I guess you're just saying it's mostly just the bandwidth cost. Like you're ignoring essentially it's ignoring the CPU cost.
Yeah, I guess the way to say it is in certain scenarios that's true. So on AWS that's true. Like in the AWS scenario, the cost of streaming a movie, you can use a lot of CPU and never make a dent in the total cost. I should keep going maybe. It might we at the end we do some experiments that I can share more details. So I'll talk about the construction now. So the way we construct this scheme is we kind of a traditional way. We compose 2 lattice-based homomorphic encryption schemes, which we call Regev and GSW. the naming is a little, yeah. The Regev scheme that we use has high rate and fast operations, but for our purposes only supports homomorphic addition. So we only use it with homomorphic addition. And the GSW scheme has much lower rate and slower operations, but supports homomorphic multiplication. Specifically, it kind of plays nice with the Regev scheme. So you can multiply a GSW ciphertext by a Regev or GSW ciphertext. And the point is that that homomorphic multiplication has only additive noise growth. So we're going to exploit that to build PIR. So I'll just kind of review like Regev and GSW encodings at a high level kind of quickly. If we want to come back and talk about it more, we can. But basically, a Regev encoding of a scalar, here we're operating in rings. So a scalar is a single ring element. What it does is let you recover a noisy version of the original message. So that's why we call it an encoding scheme, not necessarily a ciphertext. We're just saying here that when you multiply the secret key by the encoding, you recover some noisy version of the message ring element. And if you want to actually support decryption, like correct recovery of a single message, you might choose some smaller modulus P, smaller than Q, and then encode the message as mu times Q over P. So you would basically scale, right? And then decryption is essentially rounding, right? You do this multiplication and then you round to yield mu. It's good to note here that in this scalar setting, the rate is actually upper bounded by 1/2, right? Because we need to transmit at least 2 ring elements, and not only that, but we're only transmitting p bits of information, but we have to, the ciphertext is composed of q bits per ring element. So the rate is significantly less than 1/2 in this scenario. So later work kind of like noticed that you can essentially amortize the randomness in the first element of that 2-element encoding. So this is sometimes called also PVW, but basically you can also encode matrices this way, and it's a pretty natural extension. Basically, instead of a scalar, there's now an n by n matrix that we're encoding, and the rate is now basically scaled with n squared over n squared plus n. So what that means is like as n gets larger, the rate is approaching log p over log q. So now it would be possible to now have a rate that's larger than 1/2 in the matrix setting. And I'll point out, you know, both of these schemes are additively homomorphic, right? Just immediately. I guess just a note on the amortization thing, that just to emphasize that the secret key is now in this matrix setting a vector of scalars, and so the idea is that we are amortizing in the sense that there's only one pseudo-random element and then multiple secret keys that are constructing the encoding column-wise. So in contrast, let's look at the GSW encodings. Here we have the same kind of matrix-style secret key. The encoding now has m columns, and the encoding, we actually only consider encoding bits in GSW. So we just consider a mu that's a bit. And here we have a gadget matrix and the secret key embedded in the message. So just what that gadget matrix is, it's this powers of 2 matrix. And it's useful to note here, the rate is very low. So to encode a single bit in GSW, we need you know, a lot of stuff. We need the entire, we need m columns, where m is n plus 1 times log q. Concretely, it's like megabytes. So this GSW encoding is very large just to encode a single bit. But there is a point to it. There's a reason that these are useful. And the reason is the gadget matrix has this nice property that it's easy to find what we call like a gadget inverse of a vector, where the gadget times the gadget inverse recovers the vector, but the gadget inverse is only composed of elements that are bits. So here I've shown binary decomposition, and in the slides it's all binary, but of course you can use a base other than 2, and then the gadget inverse will have elements, you know, of that base. And the point is, we actually do use many different bases in our construction to achieve like noise growth that's better. So yeah.
Can I ask one last question about the 2x? Sorry.
Sure, sure. No, it's okay.
So you're storing everything in memory. So the EBS reads and disk reads and writes don't cost you money. Because I remember the EBS operations are pretty expensive.
Yeah, okay. So I will say, yeah, we don't cost this out, I think, at the full, like if I was going to OSDI and trying to like really cost this out, I would agree that we don't, for example, you're right, cost memory. We don't even cost memory bandwidth, which is like, those are kind of separate too. We've reduced our cost model is just communication and CPU seconds. So we are ignoring that cost.
Okay, sounds good. Yeah, thanks. Okay. Yeah, I think it's quite interesting that it's 2x.
Yeah, we thought so too. I think yeah, it was an exciting kind of, yeah. So the point of these ciphertexts is that there's this homomorphism between them, also called the external product. I'll just kind of highlight exactly how it works. You multiply the GSW ciphertext, in this case on the left, by the gadget inverse of the Regev one. And the point is you get a recovery of the bit times the message that the Regev encoding was containing. And just to show you it with the actual noise terms, because it's actually a very kind of weird noise growth pattern, there's a very asymmetric noise growth, right? So if all the GSW ciphertexts are fresh, the accumulation is linear in the number of times we multiply by bits. So if we have, say, 5 bits, and we multiply a ciphertext by 5 bits repeatedly, the ultimate noise is actually only linear in the number of bits we multiply. So if you think about it, I guess this is maybe getting like a little ahead, but we are indexing an exponential number of bits, right? Like we're indexing an exponential number of items. Like for L bits, we can index 2 to the L items, and we only incur noise linear in L. So that's really powerful. That's very useful for PIR, and I'll show how we use that. So there's a prior work that does exactly that uses both these schemes to do PIR, and I'll explain it here. It's called Gentry-Halevi from 2019. So in this prior work, the query is composed of Regev and GSW ciphertext encoding bits, and the point is that we can use the Regev ciphertext. I'm going to show I'm showing the database as a 4x4 matrix of plain text, and the star element is the one we want to retrieve. We can use the Regev ciphertext to select along the first dimension. And the point is here, we're multiplying a vector of ciphertext by a matrix of plain text, right? So we're selecting this second row. And since the ciphertexts are being multiplied by plain text, that's not really a multiplicative homomorphism, right? That's just scalar multiplication. So it's okay with Regev ciphertext. And we'll get as output that target row that we were aiming for, right? The point here is this operation is very fast because the matrix Regev ciphertext multiplication is it supports fast homomorphisms. So now we have these 4 intermediate matrix Regev ciphertexts, right? And we would like to just select the one that we want. So now we use the GSW ciphertext to select. And the way we do that is, since we've encoded as in bits, the kind of halves of each level that we want, we call this like folding. Basically, at each round, we use a single GSW bit and its complement to have the number of ciphertexts that we're working with. So the first time we multiply, these 2 ciphertexts on the left by this GSW bit of 1, and the 2 ciphertexts on the left by this GSW bit of 0, and we get the 2 ciphertexts on the right. And we can keep doing that until we're left with only a single ciphertext. So this is called folding. We only incur noise in the number of levels of folding that we do, so we don't incur that much noise. It's very useful for improving the rate. Prior work would just send that intermediate vector directly, but of course then the rate is not very good. So the result is a matrix Regev ciphertext. So now it has high rate because we said that earlier, the amortization is better, the rate is very high. So this is actually a very good scheme. They didn't implement it, so we can't say for sure whether it would have been fast or not, but it seems like it would have really been good. There was only one downside, which is that you have to communicate these GSW ciphertexts, and those are very, there are 1/2 log n GSW bits. Yeah, so sorry, there's a question in the chat about how many GSW bits there are. The exact way you structure the database is kind of a parameter that we can choose. So we could make the first dimension very large, and then we could fold very little, or we could make the first dimension smaller, and we could do more rounds of folding. So it's a parameter. So anyway, the downside is that the GSW bits are very, very large, megabytes each. So the query becomes large. It's not very practical. There's another work that basically addresses this called Onion PIR. They show how to take a scalar ciphertext and expand it into scalar Regev and GSW ciphertext. And then they show how to kind of assemble from a scalar Regev ciphertext a GSW one. But the point is that all of these ciphertexts and all their transformations are operating on scalar ciphertext. So the output is a scalar ciphertext, which means that the rate is not very good. So the rate is only 0.24 in this other work. So they achieved the small queries. Their query is only 64 kilobytes. But then the rate, meaning the ratio of the record size to the response size, is very small. So the point of our work is to get both of these. We want the best of both worlds between these two prior works. We want the small queries of Onion PIR and the high rate that are in Gentry-Halevi. We introduce new techniques to compress both the query and the response to achieve this. We show how to compress the query using transformations that let us do conversions from Regev to GSW in non-scalar in n greater than 1 contexts. And we show how to compress the response further using packing and a better modulus switching technique. Basically, the high-level takeaway is we get the benefits of working with these massive ciphertexts, but we don't have to actually communicate them. And we think some of our techniques are probably of general use even outside of PIR. So just at a high level, here's what Spiral looks like. On the left, we do query expansion, just like Onion PIR. So we have small queries, and then we expand to the ciphertext that we want to use. We process using matrix ciphertext, so we get high rate because the output is a matrix ciphertext. And we introduce new techniques that are kind of not in either prior work to compress the response. So that's the overview of the scheme. I'll show you how two of these transformations work. Since we're running short on time, I won't get into like the super detail about it. I'll kind of skim these slides a little bit. So we show how to take a scalar ciphertext and transform it into a matrix one. And the way we do that is basically we notice that this is a slightly different framing of how we frame it in the paper, but it's equivalent. Basically, we show that you can concatenate encodings and then just do a generic key switch. So basically, you can get an encoding under one key that is the matrix form, but you just need to do a single standard key switch to get the encoding under an arbitrary key. So essentially what we show here is, if you imagine that S2, the matrix key, was of this special form where the secret vector was all the same element, then you can actually just construct the ciphertext that you want directly from the scalar one, and then you just need a standard key switching. So what this does is let us take an encoding of some message M and produce a matrix encoding of M times the identity, times I sub n. So the Regev to GSW conversion is more complicated, so I will go more in depth on it. So basically, here, what we want to do is construct from some Regev encodings, which I'm leaving a little undefined what the input is to this procedure. We want to use them to construct a GSW ciphertext. So we want to construct a ciphertext that encodes this message mu SG, right? So that's our goal. I'm going to show how to kind of work backwards from the goal a little bit. So first, I'm working backwards from the goal here. First, recall what the gadget matrix looks like there, right? This is our powers of 2 matrix. I'm going to rearrange the gadget matrix. You should be convinced that this doesn't really change anything. The gadget inverse is still applies if I just permute the columns of the gadget matrix. So all I've done here is I left the first t+1 columns fixed, and then I just permuted the rest of the columns so as to form this kind of, on the left, I just have the standard GT there, like the standard powers of 2, and then on the right, I have a bunch of submatrices that are just like the identity matrix scaled by powers of 2. So this will help me explain kind of how our construction works. So I'm just rearranging. The rearrangement is reversible, so it's all equivalent. So looking at this kind of permuted gadget matrix, we can see our goal is to construct mu SG, and mu SG looks like this. So we have these blocks that I've colored. We need to construct each of these. We need to construct encodings that encode each of these values in turn. So I've named what we need to construct A and B0 through BT. And you can see, we're breaking this up column-wise, right? And the columns are all just columns in Regev encodings. In either of these encoding schemes are just concatenations, right? There's no interaction between the columns. So we can just construct encodings for the values A and B0 through BT separately, and then we can concatenate and we'll form the encoding that we want. So our goal is to construct A, B0 through BT that equals the values right above it there. So I'll start with the kind of easy one. The easy one is we want to construct B0 through BT so that we get mu times the identity matrix, 2 times mu times the identity matrix, 2 to the 2 times mu times the identity matrix. Basically, we want the powers of 2 scaled by the identity matrix times mu, the bit mu. So say we were given a bunch of scalar encodings of the bit mu multiplied by 1, 2, and so on. Then it would be a direct application of our previous technique, right? We have a bunch of values, and we'd like to just get encodings of those values times the identity matrix. So we can apply our scalar to matrix technique to construct those kind of immediately. This part is harder. So we also want to construct a matrix A that kind of includes this secret vector that's in the matrix key S, this little s there, times the powers of 2. So to do this, we have to actually use a kind of key switching. And the key switching that we use is a little funky looking. So we publish this matrix W, which encodes actually kind of 2 secret keys. One is the secret vector, the first column of the GSW key, basically. And the other is the key that the input Regev encodings are under. And so we show that if you publish this matrix, it kind of works out. So again, given those same encodings of mu times the powers of 2, you can just apply this single key switch and construct what we want, this mu times little s g. So this is how we get A. So this is how we construct A. We publish this key switching matrix as part of the public parameters. So the client has to send them at the beginning, and then the server can use that key switching matrix to construct this component A. So just to review how the transformation works, we use this W matrix, this key switching matrix, as part of the public parameters to construct the A component. We use our previous technique, the scalar to matrix transformation, to construct these scaled identity matrices, and then we can concatenate and form a GSW encoding of the bit mu. And again, if we wanted to go back to the other gadget matrix, we could permute the columns at this point and get what we want. So what we've done, I mean, ultimately what this transformation does is, if you look on the left, right, we only send 2 times t+1 ring elements to communicate this, right? Because there are t+1 values we need to communicate, and each encoding takes 2 elements. But we have constructed a GSW ciphertext that would have otherwise taken n+1 squared times t+1 ring elements. So you can see for any n, this is already some savings, and for larger n, this will be a larger savings. But there's a real reason we're doing this that is a much larger factor of compression, which is this known technique. So there's a known technique to take, if you want Regev encodings of many values in ZQ, so like many just integers, mod Q, then you can actually pack all of those values into a single encoding of a single polynomial, and then you can use this known technique to extract Regev encodings of each of the coefficients separately. It uses automorphisms, and like the point is like you can kind of use like almost like a destructive interference type thing to like slowly zero out the other coefficients and just get an encoding of each coefficient separately. This is a known technique, but what this does is this takes us from 2 times t+1 to just 2 elements, right? Because now we can encode those mu times 2 times mu, we can encode, we want the encodings mu, 2 mu, and so on. And now we can put all of those in the coefficients of one polynomial, as long as t is less than d, basically. So t, remember, is log q. So this is almost always true. I mean, the log of the ciphertext modulus is much, much smaller than d, the dimension of the ring. So the ring is like 2048 coefficients, right? And t is like, for security reasons, t cannot be already larger than much larger than like 56. So this is almost always true. You can pack all of the stuff you need for a GSW ciphertext into just 2 elements, and then perform this kind of efficient expansion afterwards. And our noise growth in the expansion procedure is quite good. So ultimately, this is actually a very useful way to compress GSW encodings. So as an overview, this is how we compress the query. We actually pack everything into a single scalar ciphertext, just like in Onion PIR. But our outputs are all matrix ciphertext. So that's what's different about the work than Onion PIR. So here's the summary of how we compress the query. Okay, I'll just talk about response compression briefly. So we introduce more than one technique for response compression, but I'll talk about one. This is modulus switching. We make like a very simple observation that I think is kind of cool. When you want to finally send the response, you have this matrix encoding of a matrix, right? And so the rate scales with log p over log q, right? As long as you choose a kind of sufficiently large n, the rate is about this, right? So a standard technique in FHE is to do modulus switching. So at this point, you can switch the ciphertext down to some smaller modulus q prime, but you incur some rounding error. So basically, the switching incurs like an error that is scaled by the secret key. So you have some rounding error with that's uniform and less than 1/2, and it's multiplied by the secret key. But there's a cool observation here, which is that the secret key, only the first column of the secret key has like elements sampled from the noise distribution, or if you're in the standard LWE context. The rest of the secret key is just the identity matrix. So what that means is different parts of the ciphertext actually contribute very differently to the noise. So if you scale the first row, if you scale all but the first row of the ciphertext very aggressively, it does not impact the noise growth. It does not incur the same amount of rounding error. Basically, the first row is special, and you should preserve more information about it. And the rest of the rows are only contributing additively to the noise. So the rounding error is very small when you switch down to a very small modulus. So this is like a very, very useful observation. You can make the small modulus, the one that you use for all but the first row, Q1 in this slide, you can make it really, really small. So you can make it actually, in this example I've shown, it's only 2 bits larger than the plain text modulus. The modulus for the first row is going to be the same as what you would have had to do if you had switched the whole ciphertext to the same modulus. So anyway, this is like a huge win for the rate. The rate goes up by a lot if you do this split modulus switching technique, especially if you also use a large matrix. Especially if your n is very large. So you can see the rate goes up by a lot here, and I've shown some comparison schemes. Oh, sorry. Yeah, so the takeaway is this actually incurs no error. There's almost no client overhead to doing this, and it increases the rate a lot. So basically, anytime you communicate matrix Regev ciphertext, you should probably do this. You should probably switch all but the first row to a much smaller modulus than you would have. So there are two other tricks that are I'll talk about. The first is how we choose parameters. There's a ton of parameter choices you can make. You can use different decomposition bases in different parts of the query expansion. You can arrange the database so that the first dimension and the second dimension are different. And you can play with the plaintext modulus and the size of all the matrices that you use. To choose our parameter systematically, we wrote a script that basically, for any set of parameters, guesses estimates how long it thinks query processing will take, and then comes up with a cost from that. So it uses the AWS cost model, and then it just chooses the set of parameters that it thinks will minimize AWS cost, basically. We think this probably helps us be more efficient and not just kind of randomly choose parameters or choose ones that we think work manually. The input to this tool is the dimensions of the database you want to serve. The other thing we do is we choose the ciphertext modulus in a kind of special way. So I won't get into the super big details, but basically, if you choose the ciphertext modulus and use CRT well, you can exploit AVX2 and AVX512 like SIMD instructions on the CPU to do lots of throughput, to do lots of computation faster. And this gap between the 56-bit modulus and the 64-bit integer width on the CPU is very useful because it means you can accumulate. We're doing a lot of matrix vector products, right? So you want to accumulate results without actually invoking like modular reduction, even Barrett reduction. So this gap is very useful. You should not, modularly reduce every time you multiply two coefficients. You should like accumulate in 64 bits and then only reduce when you absolutely have to avoid overflow. So that gives us another kind of win. So I'll talk about the results. We, on a one big benchmark database that people use is 1 million records and 256 bytes each. That's because it gets used a lot in like metadata private messaging contexts, where the messages are assumed to be kind of small, like 256 bytes. And even on this kind of benchmark, you can see we do better on query and response size. Our compute is actually not the winner. FastPIR has a lower compute, but the query is 33 megabytes versus our 14 kilobytes. So, you're paying a lot for the slightly faster query processing. And you can see our public parameters are larger than previous work. So that's the trade-off. Our scheme incurs more public parameters. And you should also note, across the board, none of these schemes do well, really, in terms of response size. To fetch 256 bytes, all of these schemes require you to fetch, at least 20 kilobytes. So, we're not that great yet when the records are small. And that's because lattice ciphertexts are just large. That's the smallest lattice ciphertext to encode the smallest possible information still encodes kilobytes in our scheme. We also choose the database configuration preferred by the best prior work, onion PIR, and we do better on these 3 key metrics like we saw before. And you can see I've phrased the performance in rate and throughput there, and you can see there's like a 50% increase in the rate and about a doubling of the throughput at the cost of about 4 times larger public parameters. We also have a graph of like how the system performs when we fix the record size and change the number of records. You can see, indeed, as we said before, the processing is linear in the database size. There's kind of a little bit of change at 2 to the 14 because there's some fixed costs on the left of the graph. At this kind of linear portion where our throughput, even with query expansion, is already about 300 megabytes per second, which is roughly the same speed as software-based AES. It's not shown on the graph, but the query size and response sizes are smaller, but the public parameters are larger. And you can see how the other systems perform here too. This is kind of, I'll say this quickly, our client costs are very similar to other schemes' client costs. The most expensive part is setup, where we're doing a lot of key gen and we have to sample a lot of randomness. The query generation is fast, and so is the response decoding. We consider another setting, which is the streaming setting, which I mentioned before, which is where you fix a query and you have multiple databases. This comes up in video streaming, but also in private messaging, where you kind of like might choose a mailbox and then you might like repeatedly fetch from like the mailbox over some time. So if you think about it, that's like we're keeping the query fixed, but we're changing the database. So here, it actually makes sense to just focus on the compute and response sizes and kind of ignore the public parameter and query sizes, because these are amortized over the whole lifetime of the stream. So even if you say perform 10 or 100 of these, already these costs are amortized away very quickly. So we explore how does the scheme perform if we perform less query expansion and actually just directly upload the encodings. We just removed the first expansion, the Angel et al. Coefficient expansion procedure. That significantly reduces the noise growth. Our transformations actually we keep because they don't take time, they don't take much time, and they don't incur much noise. Basically, as you know, when you reduce the noise, basically everything gets better, right? The throughput and the rate go up because there's less noise growth, and we can use a larger plain text modulus. The downside, of course, is now we're uploading a lot more because we aren't getting that expansion, or we aren't getting that query expansion step. So the queries are much larger. So in this streaming setting, we analyze the schemes slightly differently. The way we look at it is we just focus on throughput. So we just say, what are these PIR systems throughputs? We assume the best possible record size for each system, and we ignore the cost of expanding the query, since that only needs to be done once. And you can see, yeah, SPIRALSTREAM is roughly 3x faster, or 3x higher throughput than Spiral. And it peaks at around 1.5 gigabytes per second, which is 7 times faster than all previous constructions. You can see the query size is 30 megabytes. So think about that. We paid a 2000x increase in the query from 14 kilobytes to 30 megabytes, right? And we got about a 3x improvement in the throughput. So 2000 times larger query, 3x improvement in the throughput. So that's the kind of trade-off we're dealing with. This can still be worth it. And the rate for the scheme is also much higher. The rate is now already 50%. A question we ask is, can we get a rate that's higher than 50%? We want to, the fastest way to get a rate higher than 50% would be to use a larger N, but unfortunately that lowers the throughput, because now all our matrix multiplications are with this larger N. So our idea is to run one of our transformations almost kind of in some ways backwards, or in a different way, which is we want to take many scalar ciphertexts. We want to do all the processing with scalars and then pack them all into a matrix at the end. Because the only reason we want a matrix is not for processing, it's just for that last communication over the wire. We want everything to be in a matrix ciphertext to get higher rate. So we actually show you can use this. We construct another transformation called packing, where we take many scalar encodings and pack them into a matrix one. This is different than taking a scalar encoding and getting an identity matrix encoding times that scalar. So this is kind of like similar, but not the same. This packing procedure basically works like this. We show how to kind of place it in the column and then add and concatenate to form a matrix encoding. The high level takeaway is just like it requires more public parameters, but we can now get the best of both worlds again, where we use scalars for processing and we communicate this packed encoding on the wire back. So packing is like a straight, simple improvement in throughput and rate for most scenarios, but the downside is that the public parameters are larger. So you can see the dotted lines are the packed versions of both Spiral and SPIRALSTREAM. And this is where we get like the top line number of the 2 gigabytes per second and the rate of 0.81. So the public parameters are very large at this point. They're 125 megabytes. So yeah, that's a real cost that you're imposing. And the query is also very large. So basically, yeah, at a high level, the packing allows us a higher throughput and rate, but with larger public parameters. And it's this scheme that we use to compute that metric about the 2x more expensive than the no privacy baseline. So the best possible previous scheme under this cost regime was about 17 times more expensive. So we also think it's a significant improvement over prior work. And yeah, just the future directions we're looking at. I'm interested in kind of maintaining the library. I hope that it gets used in other systems. I know that PIRs, I've wanted a PIR library before. I think that our techniques for FHE composition might be applicable to systems other than just direct PIR. We would like to perform better for smaller record sizes. There is that cool new pre-processing work from Henry Corrigan Gibbs and Alexandra. So that would be cool. We have to see how practical we can get it. Yeah, there's been some interest for people to just like use PIR directly. So some people are interested in it for certificate transparency, DNS, etc. And yeah, so there's the demo, there's the paper, and there's the code. So thank you so much. I'd love to take any questions. I know we're kind of towards the end, but.
Can I ask questions? Can you hear me?
Yeah.
Oh, so I think the main takeaway from your paper is that you are not directly changing the PIR algorithm, but you are changing how you like transmit the ciphertext of those FHE things. Right?
Sure. Yeah. I agree. So we didn't change a lot about how processing happens. We changed how we expanded the query and also how we pack the response.
Oh, okay. And the second question is, can this technique be used in like batching setting, like in SPIR?
Yeah. So there's a number of batching constructions that are basically generic with respect to the underlying PIR. So we haven't explored those or even something less generic. I think something David's very interested in is looking at the Angel et al. Like reverse cuckoo hashing type thing, and also the we also are interested in the sparse random linear codes kind of approach to batching to allow clients to fetch multiple items at once. But we have not explored that.
Okay, thank you.
Okay, I guess if there's no other question, let's thank Samir again.
Thanks so much.